Electric dipole. An electric dipole is a pair of equal and opposite point charges placed at a short distance apart. The product of one of the charge and the distance between the charges is called electric dipole moment. That is, vector P is equal to Q times 2L, where 2L is the length of the dipole. Remember, it's a vector quantity. The direction of electric dipole moment is from negative charge to positive charge along the line joining them. For example, a water molecule, that is H2O, is an electric dipole. Similarly, an HCl molecule is another example of an electric dipole. So let's work out the first derivation, that is to calculate electric field due to an electric dipole in and on position. So in this situation, if we take a point towards the right side of this dipole along the axis of the dipole at the point P, which is at a distance r from the midpoint of the dipole, the electric field due to positive charge is towards the right side at the point P, and electric field due to the negative charge is towards the left side. So first, if we calculated the electric field towards the right side, it is 1 upon 4 pi epsilon naught times Q upon r minus L whole square, because distance of B from P is r minus L. Similarly, electric field due to negative charge is 1 upon 4 pi epsilon naught times Q upon r plus L whole square, because distance of A from P is r plus L. So now net electric field at the point P is given by E1 minus E2, because E1 will be greater than E2, because distance of P from the second charge, that is positive charge, is smaller as compared to the negative charge. Therefore, electric field due to positive charge is greater. So we are calculating the net electric field here, that is E is equal to E1 minus E2. Substituting the two values and taking out 1 upon 4 pi epsilon naught as common, we get Q upon r minus L whole squared minus Q upon r plus L whole squared. Simplifying this by taking LCM and calculating the values in the numerator, we get Q over 4 pi epsilon naught times 4 RL upon r square minus L squared whole squared. Now the net value of E becomes 1 upon 4 pi epsilon naught times 2 PR over r square minus L square whole squared. Here P is the value of 2QL, which is electric dipole moment. If R is very large as compared to L, then E is equal to 1 upon 4 pi epsilon naught multiplied by 2P upon R cube, because in that case we put L equal to 0 in the above equation. So this way we have obtained the expression for electric field in and on position. Now let us find out electric field due to an electric dipole in broad on position. In this situation, the point P is taken on a line perpendicular bisector of the points joining A and B. Now in this situation, at point P, electric field due to B is away from B at point P, and similarly due to negative charge at A, electric field is towards that negative charge, that is denoted by a blue arrow. Now in this situation, electric field due to positive charge at point P is 1 over 4 pi epsilon naught times Q upon r square plus L square. R square plus L square is the length of PB whole squared. Similarly, E2 is 1 upon 4 pi epsilon naught times Q upon r square plus L square, because the length of PA is also equal to PB. So, in this situation, if we wish to calculate the net electric field at point P, components of E1 and E2 parallel to AB are being in the same direction, and that is why we are going to add up these two components, but the vertical components of these two electric fields, which is vertical from P and downwards from P, will cancel each other. So, the net electric field at point P will be sum of the horizontal components that are parallel to AB in this situation, that is E is equal to E1 cos theta plus E2 cos theta, but E1 and E2 are equal in magnitude as we can see above. So, this becomes twice of E1 times cos theta. Now, if we substitute the value of E1 and put aside 2 cos theta, we get 1 upon 4 pi epsilon naught times q upon r square plus L square multiplied to 2 cos theta. Now, let us work out the same situation in forward. If we put the value of cos theta from the triangle POB, so cos theta will be equal to base upon hypotenuse. So, this becomes L over under root r square plus L square. So, substituting this value and simplifying, we get 1 over 4 pi epsilon naught times P upon r square plus L square whole raised to the power 3 by 2. The numerator becomes P because this is now product of Q and 2L. Also, the direction of this electric field is anti-parallel to the dipole moment. If again we take R, which is very large as compared to L, then the value of electric field becomes negative of 1 upon 4 pi epsilon naught times P over R cube. Here this negative sign indicates that the direction of electric field is opposite to the direction of electric dipole moment. So, this way we have derived an expression for electric field due to an electric dipole in broad on position. Torque on an electric dipole placed in a uniform electric field. If an electric dipole is placed at a certain angle with uniform electric field, then the positive charge experiences a force in one direction and negative charge experiences a force in opposite direction. If we drop perpendiculars from these 2 points and consider this angle to be theta with the base and the length between the two charges, the distance between the two charges is 2L. So, the perpendicular distance of the two forces is 2L sin theta, and we know that torque is given by force multiplied by perpendicular distance between the line of action of the two forces, and we substitute the expression for force, that is QE, and the perpendicular distance, that is 2L sin theta. So, this expression becomes torque tau is equal to 2QL times E sin theta, and we know that expression for 2QL is actually equal to P, that is electric dipole moment. So, expression for torque is equal to PE sin theta. If we write the same expression vectorially, its vector tau is equal to vector P cross vector E. Remember, in this situation, as we have written, torque is equal to PE sin theta. So, this value of torque will be maximum when sin theta is 1, that is when theta is 90 degree. Therefore, torque is maximum, which is equal to P times E, and in this situation the dipole has been placed at an angle of 90 degree with the uniform electric field.